Hey, and welcome to The Explainer. Today, we are diving into one of the most powerful and frankly, coolest ideas in modern AI, contrastive learning. It's this amazing technique that's totally changing how machines learn to make sense of the world, basically by teaching themselves.
So let's just start with this massive question. Think about it. The internet is flooded with billions and billions of images, videos, and chunks of text, but almost none of it has labels. So how on earth can an AI learn from all that chaos? How does it figure out the difference between a cat and a car if nobody's there to tell it, hey, this is a cat? Well, the answer is actually a beautifully simple idea: learning by comparison.
So here's our game plan for this explainer. We're going to cover learning without labels, then we'll peek under the hood at how the magic works. We'll look at the rules of the game, see it all in action, and then wrap it all up with your key takeaways. Let's jump in.
Okay, first up, learning without labels. At its core, contrastive learning is built on an idea that's just really human. It's how we learn, right? We figure out what something is by comparing it to what we already know.
So here's the official definition. The whole goal here is to teach an AI to create what you can think of as a smart map of all its data. And on this map, things that are alike get grouped really close together, and things that are different get pushed way, way apart. The trick is giving it pairs of examples to compare.
And this is the crucial part, this whole push and pull dynamic. A positive pair might be two different pictures of the exact same cat. The AI gets a simple instruction. Hey, these two are similar. Pull them together on your map. Then you show it a negative pair, say a picture of that cat and a picture of a car. The instruction changes. Nope, these are totally different. Push them far apart. And by doing this millions and millions of times, it starts to build a map that actually understands the concept of what makes a cat a cat.
Now, there are a couple of flavors of this. There's the supervised kind, which uses data that already has labels. But the really interesting one, the one that's a total game changer, is self-supervised. This is where the AI gets super clever. It starts making up its own little learning games. For instance, it'll take a single image, maybe crop it and change the colors to make two slightly different versions. And then it gives itself a challenge. Recognize that these two variations are a positive pair, and literally everything else is a negative. That simple trick is what unlocks its ability to learn from pretty much the entire internet.
Okay, so we've got the what. Now let's get into the how. How does the AI actually build this smart map of data? Let's walk through the process, step by step. So it all kicks off with data augmentation. That's where it creates those different views of the same image to make a positive pair. Next, an encoder network, which is basically a feature extractor, looks at each image and boils it down to a bunch of numbers. That's its first location on our map. Then a projection network refines those numbers, helping the AI focus on only the most important features for comparison. And finally, the contrastive objective gets applied. This is like the magnetic force that pulls the good pairs together and shoves the bad pairs apart, just constantly organizing that map until it makes sense.
But wait a second. How does the AI know how hard to push or pull? How does it grade itself? Well, it needs a rule book. In machine learning, we call that a loss function. Let's just think of it like this. A loss function is basically a coach for the AI. It's not telling the AI what a cat is, but it's telling it if its guesses are getting warmer or colder. It calculates a penalty score for how messy the map is, and it rewards the AI for making good moves, placing similar things together, and penalizes it for bad ones. The AI has one single goal: get that penalty score as low as you possibly can.
And just like different coaches have different playbooks, there are different loss functions. You've got triplet loss, which is a classic. It looks at three things: an anchor image, a positive, and a negative, and its only job is to make sure the positive is closer than the negative. Simple. Then there's n-pair loss, which levels up the game by comparing one image to a whole bunch of positives and negatives all at once. And one of the most popular ones today is infoscene's loss, which brilliantly turns the whole problem into a multiple-choice quiz. Out of these 100 images, can you pick the one that matches?
So we've got the theory down, but what does this actually unlock in the real world? This is where you see the true, incredible power of this idea. This isn't just some academic thing. It's a foundational piece of technology. Just stop and think about this for a second. Over 75% of all the data in the world is just raw, unstructured stuff. Photos, videos, text with no labels. For decades, it was all just digital noise. Techniques like self-supervised contrastive learning are what finally gave us the key to tap into this gigantic resource and turn all that noise into actual knowledge.
And its impact is everywhere.
It gives a massive boost to models when you only have a tiny bit of labeled data to work with. In language, it helps models understand that the king sat on the throne and the monarch was on the royal seat basically mean the same thing. It's a total game changer for computer vision, and it's the engine behind something called transfer learning, where a model that's been trained on a billion internet images can be quickly retrained for a super specific task like identifying cancer in medical scans.
All right, we've covered a lot of ground. So let's bring it all home and focus on the 3 most important things to remember about all this.
Number 1, it learns by comparison. At the end of the day, forget all the complex jargon. The big idea is just to group similar stuff and separate different stuff. That's it. Number 2, its superpower is unlocking unlabeled data. That's what makes it so incredibly scalable and powerful. And finally, remember that contrastive learning is really a foundation. That smart map it builds usually isn't the final product. Instead, it's an incredibly powerful starting point that makes all kinds of other AI tasks way easier and way more accurate.
So I'll leave you with this. If AI can now teach itself to see deep patterns and understand complex concepts just from the messy, unlabeled data of the real world, just by observing what's similar and what's different, what new frontiers of science, medicine, and creativity is it going to help us unlock next? It's a pretty